In this lecture, we discuss PIN diodes and control circuits. So, a PIN diode, it contains an intrinsic or lightly doped layer in between P and N layers, and that is why the name of this diode is PIN. Addition of intrinsic region, it reduces the junction capacitance, since P and N regions are now further apart. Introduction of this intrinsic region also makes forward conductivity of the diode a much more linear function of diode bias current. Under reverse biased condition, the diode impedance becomes high due to a small series junction capacitance, whereas under forward biased condition, the junction capacitance is not present and the diode is in a low impedance state. So, this is in brief how the diode behaves under the reverse and forward bias conditions. We represent an approximate equivalent circuit for such diode under reverse and forward biased condition as shown in the figures. So, this is the diode simplified equivalent circuit. So, we have Li as the inductance of the lead, Cj is the junction capacitance, and Rr is the resistance of the device under reverse bias condition. In the forward bias condition, as we have said, this Cj is not there and the resistance value of the device also changes and it is represented by Rf, and therefore, the equivalent circuit becomes Li in series with Rf. Now, since this device offers high impedance in the reverse bias state and low impedance in the forward bias state, therefore, this device can be used as a switch and the impedance of the device can be controlled by changing the bias of the device, and therefore, switching action can be obtained. We will start our discussion with a single pole PIN diode switch. This is also called SPST, single pole single throw. So, we consider a single pole single throw or SPST switch, the schematic of which is shown in the figure, and this is a series switch because here the diode element, it is connected in series. We can see that this diode is inserted between transmission line and we have this P side of the diode is connected to the bias through an RF choke. The purpose of this RF choke is to provide a high impedance for the signal, and at DC this inductor will be a short circuit. So, this choke will prevent flow of signal towards the bias source. Also, we have a DC block here, because this DC voltage should not go to either source or to the load. So, we have DC blocks. Similarly, the N side of the diode is grounded through another RF choke. So, this will prevent the signal from going to ground, rather when this switch is on or the diode is in a low impedance state, signal will flow from the source towards the load. A simplified equivalent circuit without these biasing arrangements are shown in the figure here, and here we can see that we have a source and let 2 V naught be the signal provided by this source, Z naught is the source impedance, and this diode is connected between load, which is also Z naught. Now, this is a series switch, and as we change the bias to this diode, its impedance can be changed, either it can be made high impedance or low impedance, and essentially it will act as a series switch. Now, suppose if this switch were not there, the load were directly connected to the source, then we would have got a voltage VL, which is given by 2 V naught divided by Z naught plus Z naught, that is 2 Z naught into Z naught, that means half of this 2 V naught, that means the load voltage VL would have been V naught. When this diode is present, at that time the diode can be modeled by its equivalent impedance ZD, and the voltage VL becomes 2 V naught Z naught divided by 2 Z naught plus ZD. Now, the insertion loss IL is defined as, if you VL is the voltage when the diode is present, V naught would have been the voltage if the load were directly connected to the source. So, insertion loss is minus 20 log VL by V naught, and from this expression we can calculate VL by V naught, and once we substitute this, the insertion loss becomes minus 20 log mod of 2 Z naught divided by 2 Z naught plus ZD. So, this is the insertion loss for a series switch. Let us now consider another single pole single throw switch configuration, but this time the diode is connected in shunt, and we see that when the diode will be in high impedance state, then the signal will flow from source to load, it will not go through the diode. Whereas, when the diode is biased and it is in the low impedance state, in that case signal In the ideal case, if the diode impedance is too low, all the signals will be reflected from here and it will not go to the load, and therefore, we have a switching action here. Either the signal goes from source to load or it is reflected back by the diode and no signal reaches the load. As before, this RF choke blocks the flow of signal towards the DC bias source by providing a high impedance, whereas at DC this is short circuited and therefore, the bias voltage is transferred to the diode. In the light of this discussion, we can draw a simplified equivalent circuit as shown in the figure, and we find that ZD is now connected in parallel between the source and the load. For this simplified equivalent circuit, we can calculate VL to be equal to 2 V naught and then ZD parallel Z naught divided by Z naught plus ZD parallel Z naught, and this becomes V naught 2 ZD divided by 2 ZD plus Z naught. And once again, had the load been directly connected to the source in the absence of the diode, we would have got a voltage V naught across the load, and therefore, we define insertion loss to be equal to minus 20 log modulus of VL by V naught, and VL by V naught we can now write 2 ZD divided by 2 ZD plus Z naught. So, for both the switches, we find that when diode is reversed bias, at that time ZD is given by RR plus J omega Li minus 1 by omega Cj. This comes from the equivalent circuit of the diode, simplified equivalent circuit of the diode we discussed, and similarly under forward bias condition ZD becomes Rf plus j omega Li. So, to determine the insertion loss for the on and off condition, we need to calculate by substituting the values of ZD at the design frequency for reverse and forward bias conditions. These parameters RR, Li, Cj and Rf, these are available from the manufacturer data sheet for particular diode. So, we have seen SP-ST type switch. Now, let us consider SP-DT or single pole double throw type switches. So, this is a switch where we have two diodes and this is the input port. This input signal may be connected to either output port 1 or output port 2 by making the corresponding diode on and the other diode off. We have not shown any biasing circuitry here. So, when this diode is on and this diode is off, so we will have the signal from the input port will go to the output port 1. And for the other combination, that means when this diode is off and this is on, the signal can be connected to output port 2, and therefore, this switch gives us an action where this switch can be connected either to output port 1 or output port 2, that means it is an SPDT switch. Let us see another way in which SPDT switch can be realized. Here in this case, the diodes are connected in parallel and we are using lambda by 4 sections. So, suppose the diode in the output port 1 that is off and the other diode is on. In that case, what will happen? When this diode is on, its impedance is very low. So, ideally it is a short circuit, and this lambda by 4 section we will transform it to an open circuit at this junction, and therefore, signal will flow from input to output port 1 and no signal will flow in output port 2. Similarly, when we change the order of biasing, we make the diode connected in port 1 short and the diode connected in output port 2 open. In that case, no signal will flow to output port 1 and the signal will flow to output port 2. So, it becomes essentially a single pole double throw switch. PIN diodes can also be used in designing phase shifters. So, we see that this type of phase shifters are essentially switched line phase shifter. By switching on one set of diodes, we can bring a transmission line section of a given length between the input and output. For example, when these two diodes, the lower two diodes, they are made on, the transmission line section L1 is connected between input and output, while when the upper two diodes are made on, then the transmission line section of length L2 is connected between the input and output. At that time, lower two diodes are kept on the open condition, and therefore, when the signal travels between input and output through first path, so a differential phase shift can be produced in the signal travelling from input to output, depending upon whether it is going through transmission line of length L1 or transmission line of length L2, and this differential phase shift delta phi, it is given as beta into L2 minus L1.